Welcome back, students. This lesson is about oxidation. Welcome back, students. This lesson is about oxidation and reduction. So let's just review. In Chem 20, you would have learned something like this. You have a non-ionic equation. So copper metal is dropped in silver nitrate. You can split up silver nitrate into its ions. It dissociates. So you have copper plus 2 silver ions plus 2 nitrates makes 2 silver plus Cu2 positive, oh there should be an aqueous there, plus 2 NO3 negative aqueous. The nitrates are spectators and they cancel. So I have a net ionic equation of copper plus 2 silver ions makes 2 silvers and a copper 2 positive should be aqueous. Okay, so that is where you got to last year. We're going to expand on what that means now, because what's going on there is something's losing electrons and something's gaining electrons. Which leads me to an acronym that every chemistry teacher in the world knows. Leo the lion says GER. Loss of electrons is oxidation. Gain of electrons is reduction. Leo, loss of electrons, oxidation. GER, gain of electrons, reduction. So it's annoying that when we say the word reduce, reduction, it means gain electrons, but that's what it means. The term has stuck around from a long time ago when they didn't define things this way. People that processed metals would take a rock, so imagine digging rocks out of the ground and processing them into metals. The rock starts out as this big rock and it gets smaller in size, it gets reduced and turns into whatever metal they've refined it into. So that's where the reduction term came from, but anyway, it's now gain of electrons. Okay, so we talked about oxidation numbers yesterday. Now we're going to look at what's the uses of oxidation numbers. Here's the first thing. A change in oxidation numbers indicates that it is a redox reaction, an oxidation-reduction reaction. That should say RXN, reaction, not run. Sorry, typo. Okay, so if I assign oxidation numbers, I got plus 2, 0, plus 2, 0. And let's look at the zinc one. Zinc is going from a 0 to a plus 2. As soon as there's a change in oxidation number, that means this is a redox reaction. What does that mean? That means electrons are being transferred. Somebody's throwing away electrons, somebody's gaining electrons. Okay, as opposed to this one, look at this. When you assign all of those numbers from reactants to products, nothing's changed. H is H. There's plus 1 on both sides. Cl is negative 1 on both sides. Nothing's changed. That is not a redox reaction. It does not involve electron transfers. Okay, that's the first use. The second use is the magnitude of the change indicates the number of electrons lost and gained. So if the oxidation number goes up, we've lost electrons. I give an analogy that if you, when I was a little kid, I used to shoot these rockets up into the sky, and then I'd lose it every time. I could never find it. If the rocket goes up, we've lost it. We've lost the electrons. Then Elon Musk come around and he built these rockets that can land vertically. So if that rocket does come back down and land right in front of you, we just got our rocket back. If the rocket comes down, if the oxidation number goes down, we've gained it back. Reduction has occurred. And like in the top reaction there, the zinc and the zinc 2, the change indicates the number of electrons. When I go from 0 to plus 2, that means I've lost 2 electrons. 2 electrons were involved. And something you'll hear me say a bunch more, I won't get into it as much today, but oxidation numbers are assigned on a per atom basis. I'll come back to that later. And the number of electrons lost and gained must always balance. If I'm playing tennis, when I hit one ball over the net, that guy receives one ball. If for some crazy reason I hit 5 tennis balls at exactly the same time, that guy receives 5, assuming I'm an awesome tennis player and the balls all go over the net. Okay, let's look at this beaker. So this beaker has in it silver nitrate. So I've dissolved Ag positive and NO3 negative, and I'll just tell you the NO3 negative is a spectator, so I'll just get rid of it. And I'm going to put 2 of those in there. And then that orange strip is a copper solid strip. Okay. So what I have is 2 silver ions and a copper strip touching each other. And I'll tell you what's produced. It produces copper 2 and 2 silver solids. Okay, now we can do something cool. Watch this. Let's assign oxidation numbers. For the copper, we go from a 0 to a +2. If the rocket goes up into the sky, we've lost it. If the oxidation number goes up, we've lost electrons. Okay? So, loss of electrons is oxidation, Leo. So I'm going to write what's called an oxidation half reaction. So copper solid is turning into copper 2, and the way it's doing that is I'm throwing away 2 electrons. When I saw my oxidation number go from 0 to +2, I know that I'm using 2 electrons. The magnitude is 2. Also, copper is oxidized in this case, right? Loss of electrons is oxidation. Copper is oxidized, and this is going to drive you crazy, but it's called the reducing agent. If copper is being oxidized, losing electrons, it's causing something else to gain electrons or to be reduced, or the agent that causes gaining, or the agent that causes reduction. Okay, so it's the Ra, the reducing agent. Okay, I'll just say copper has a low electron affinity as well. Copper doesn't mind throwing away its electrons. It's like a philanthropist. It's got money, give it away. Okay, I don't remember if it's going to show up on here, but when I write electrons on the right-hand side of the equation, that means oxidation. The electrons in an oxidation equation are always put on the product side. Okay, let's look at silver. Silver is going from a +1 to 0. So if the oxidation number goes down, if Elon Musk's rocket comes back down, I've gained my electrons from +1 to 0. Okay, gain of electrons is reduction, GR. So here's my reduction half reaction. Ag positive plus that electron goes to Ag solid. Okay. Now I'm going to put a 2 around that just for this, because my reaction has to balance. If copper's throwing away 2 electrons, that means silver's got to gain 2. But silver has a charge of +1, so it can only gain 1 electron, which is why I have to have a second silver ion present to gain the second electron. So I bracketed the equation that happens twice. Okay, and now the silver ion is reduced. Gain of electrons is reduction. It's the oxidizing agent. If it's gaining electrons, it's the agent causing the other guy to lose electrons. Okay, and Ag positive isn't quite so generous with its money. It likes to get money, but it doesn't like to give it out. Okay, so it likes to grab onto electrons. Okay, now watch the screen, or watch the beaker. The Ag positives were attracted over to the copper strip. Electrons transfer. Copper throws away 2 electrons. Each Ag positive grabs an electron. As soon as that happens, the copper solid has turned into copper 2 positive aqueous. Copper solid is dissolving. And on the reduction equation, Ag positive is grabbing an electron and turning into Ag solid. It's actually precipitating as silver solid on there. And the demo I showed in class, students could see silver, it looked like silver fur growing on the copper. Okay, there's silver fibers, crystals. Okay, and the water turns blue because copper 2 ions have a blue color to them. That's the color of that ion. All right, that is the basics. You need to know those terms. Oxidation, reduction. You need to know the substance that's the oxidizing agent and the substance that's the reducing agent. You need to be able to assign oxidation numbers and figure out from oxidation numbers which substance is losing and which substance is gaining. Okay, there you go. Thanks for watching.